तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 8 on our ongoing series on mechanical measurements. Towards the last lecture, end of the last lecture, we were talking about fractional factorial design. We just started talking about it, but before that we had solved a simple problem which involved factorial design, a 2-level 2-factor experiment which involved machining process, and we were describing the results, and in those results there were 1 or 2 small mistakes. I would like to correct them before we proceed with the current lecture. If you remember, we had this earlier, and in this we have written P0 here, and this P0 will cancel off with this, and therefore there is no P0 here. In the earlier lecture, that P0 was shown here. That is the number 1 mistake, and the second mistake or second error was that there was an 8 here instead of 1, and it was a minor error, but just to make a correction so that the student does not get confused, because otherwise the 3 terms will add up to more than 100. So, with this 2 corrections, I will go back to the slides pertinent to the current lecture, lecture number 8. Initially, I am going to talk about factorial design, which we have already covered in the previous lecture. Then I will talk about fractional factorial design. We will also let you know why we do that. In fact, toward the end of the last lecture itself, we mentioned about the fact that the number of experiments will become very large if the number of factors are very large. Even with 2 levels for each factor, the number of experiments that need to be conducted to include all the effects. When I say the effects due to individual factors, then the effect due to the product of 2 factors taken at a time, and so on and so forth. If there are large number of factors, you will get factors like main factors, then you will have product of 2, then product of 3s, and so on and so forth. So, the factorial design which we talked about earlier will of course faithfully give information about all the effects, including the main effects and the factors, the product of the factors, and so on, but the number of experiments will be very large. So, the main reason we want to go for fractional factorial design is to reduce the number of experiments, and it can be done in a sensible fashion if we are able to get some information either from past experience or by study of similar processes, that some interactions may not be important. In general, it is reasonable to assume that very large number of factors coming together and affecting the outcome of the experiment, is the probability of that is small. Of course, it has to be verified if one wants to really verify the hypothesis, but many times it is all right to do that. Supposing there are n factors, all n factors are coming in the form of a product and affecting the results will certainly be much smaller than the main factors affecting the outcome of the experiment. Therefore, the fractional factorial design takes advantage of the fact that some interactions may be unimportant, and therefore we can reduce the number of experiments. Then I will, towards the latter part of the lecture, I will go back to the simple design, taking an example from fluid mechanics, where I will show that a simple design is necessary for various reasons, and I will give the basic reasons. I will work out using the one simple example to illustrate the use of simple design. Suppose I take a look, instead of in the previous lecture we had a 2-factor 2-level experiment, now I have a 3-factor 2-level design. So I will treat this as example 8. If we were to go for a full factorial design, we will see that we require 2 to the power of 3 equal to 8 experiments in all. So what are these 8 experiments? I have capital A, capital B, capital C. This is actually XA, XB, XC. Instead of that I have written A, B, C. The values, there are 2 levels, and I will choose positive here, positive here, positive here. This is one combination, all of them high, A, B, C, all of them high. Then 2 of them high, 1 low, and so on and so forth. You can see that we can create 3 columns or 3 vectors, and these vectors are of course linearly independent. That means they are orthogonal vectors. These 3 are the possible arrangement, and if you count the number of experiments, you will see that 1, 2, 3, 4, 5, 6, 7, and 8. So there are 8 experiments in this particular 3-factor 2-level design. If we want to capture all the effects, we need to do these 8 experiments. In fact, I have indicated the column vectors. What are all the column vectors which will be important? There will be the main effects, XA, XB, and XC. These are the same as the ones which are shown here. A, B, C, these are the same as shown there. The first 3 columns are nothing but the 3 sets of values for XA, XB, and XC. Then we can have interaction between 2 parameters. Parameters 2 taken at a time. You see that there are 3 parameters, and I can form 3 such products, XA, XB, XB, XC, and XA, XC. Therefore, XA, XB, XB, XC, and XA, XC, these are the 3 parameters, the 3 products, 2 taken at a time. And you can see that I can create this column by simply using this plus into plus is plus, plus into plus again is plus, plus into minus is minus, and so on and so forth. So these are products of 2 columns and written here, and similarly XB, XC is the product of these 2 columns, and similarly XA, XC is the product of these 2 columns. And I can also form a product of 3 all taken at the same time, XA, XB, and XC. That will be the product of these 3 numbers, and that is plus, and so on. If you carefully observe this table, you will see that all the columns, all the vectors represented by these columns are orthogonal to each other. That means that they are going to, the product of any 2 columns vectors is going to come out to be 0. That means that they are independent. That means that we have 8 different, 7 here, and of course there is one more which corresponds to all positives, which corresponds to the intercept parameter, which I have not included here. Therefore, 8 experiments, I will have enough number of equations to look for solution to all the parameters that characterize the relationship between y and XA, XB, and XC. If you remember, in the last lecture we had indicated the values of the factors as the corners of a square, and in fact we showed a point in the very middle and said that represents the mean. And in fact, if you have 3 factors, we require a cube to represent what is going on. So this is just similar to the square we had drawn earlier when the case was for 2 parameters. So the cube has got 8 corners, and I have deliberately given labels A, then B, and C for these 3 corners. Then ABC is this corner. ABC is not the product, it is just ABC is this corner. And similarly, I have got A prime, B prime, C prime, and A prime, B prime, C prime. Why do I do like this? Suppose you were to look at this cube from the right side, that is perpendicular to this surface. You will see that you will actually see a square right, and you will see the corners B prime, A, B, C, A prime and A. Now, that is not what I want to do. What I want to do is now to slightly do a little different thing, and that is shown in the next sketch. I am only taking 4 corners as shown here. I have a corner ABC, I have a corner A here, a corner B here and a corner C here. This is different from the previous sketch. I have got 8 corners and I am suppressing the ones with the primes A prime, B prime, C prime, A prime, B prime, C prime. I am removing those corners, or I am ignoring the presence of those corners. Then you will get A, B, C, C, B and A. Now, if you project it onto this plane, what you will see is C, B, A will look from this side and A, B, C will appear from here. Therefore, you are going to see C, A, B, C as though it is projected here, B at this corner, A as though it is projected to this corner. Therefore, when you see from one side, you are going to see a 2-factor experiment. Okay. In the case of 3-factor experiment with 2 levels, I have got 8 corners. I am going to look at only 4 corners at a time, and I am going to, what I am going to see is, when I see from this edge or any other edge, if you want, you can do that, you will see the 4 corners of a square. That means I am reducing the number of points, number of corners where I am going to take the parameters to 4. That means that I am reducing the number of factors or number of experiments by a factor of 2. So, this is called a half factorial design. The first half factorial design I get is by taking the values A, B, C, A, B, C, and of course, I will get a second one by taking B prime, A prime, A prime, B prime, C prime and C prime. Therefore, I can have 2 half factorial designs. That means that the number of experiments I am going to perform is reduced by a factor of 2. Of course, if you reduce the number of experiments, some information must be lost. So, exactly what is going to happen is seen from the half factorial design number 1, which I have shown here. So, I have plotted, I have put here the points A, points B, point C and point A, B, C, and the values of x A, x B, x C. We will come to this later on. You will see that A represents high value, B represents low value, C also represents low value, but A, B, C represents a high value. All you have to do is to go back to that sketch and see that A represents x A is measured in this direction, x B in this direction, x C in this. A is, this is the corner, from here you are going to the right side, this is high value, this is also high value, this is also high value, but this is a low value. Okay. So, you have what I have shown here is high value for A, low value for B, low value for C and A, B, C a high value. So, I can now construct 3 columns and we are going to have 4 experiments corresponding to this. So, x A will take plus minus minus, this will be minus plus minus, this will be minus minus plus and plus plus plus. So, these are 3 independent columns. You can see that if you take the product of any 2 of these columns, it is going to become 0. However, if I now multiply x A and x B, I am getting the column here, plus into minus is minus, minus into plus is minus, minus into minus is plus and plus into plus is plus. You see that this column is no different from this column. That means that x C, x A, x B product, they look similar or they look alike. That means we say that these 2 are aliased. That means that this is like an alias of this, and we say that these 2 effects cannot be resolved. X C and x A and x B are together. Therefore, we cannot resolve these 2 effects separately, and we say that these 2 effects are confounded. In fact, you can do the analysis and see that column x B, x A, x C are also confounded, x A, x B, x C is also confounded, and in fact, this x A, x B, x C, this product positive is confounded with the intercept parameter, because that is also going to be plus 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 plus. Therefore, in a half design experiment with the number of experiments equal to 4, I can only determine 4 parameters, P naught, PA, PB and PC, because PA is also containing information about XB XC product, PB also contains the information about XA XC, and similarly XC PC contains the information about this, and of course P naught will contain also this. Therefore, the price we pay for doing a half factorial experiment is to reduce the number of parameters we can represent, and that is the main problem. In fact, you can analyze similarly the number design number 2, you will see that the resulting thing is like this. Only thing is XA into XB, these two products will be minus XA XC in this case. In the other case it would have been plus XA XC, so here it is going to be just a change of sign. Actually it is calculated, it is the XA XB XC product is equal to minus 1. In the previous case the product of these 3 is equal to plus 1. That is the characteristic of these two designs. So we have two half factorial designs, and the advantage of half factorial design is only 4 experiments are needed to be performed, but we will not have the facility of representing all the 8 parameters. So I have further explained this aliasing and confounding by using, suppose I write y equal to P naught plus PA XA plus PB XC plus PC XC. These 3 terms are going to be called the main factors, and then PAB XA XB, PBC XB XC, PAC XA XC, these are the product of 2 things taken at a time, there are 3 of them, and finally PABC multiplied by XA XB XC. And if you look carefully, you have P naught, PA, PB, PC, PAB, PBC, PAC, PABC, therefore 1 plus 1, 3 such, 4, 3 such, 7, 8. 8 constants are there, and it is not possible to resolve all of them, because I have also shown P naught with 2 bars on the top, PABC XA XB with 2 bars on the top. That means that these 2 are confounded. We cannot resolve these 2 separately. The effect of these 2 are going to be intertwined. Similarly, PA XA and PBC XB XC, these 2 are confounded, and so on and so forth. Therefore, what it means is that only the main effects are resolved, and the terms that are confounded, which are indicated with the bars here, are not going to be resolved separately. So this is further brought out by seeing that the model which we can have for this particular case is a linear model, y equal to P naught plus PA XA plus PB XB plus PC XC, and what is possible is all this. That is, I can only have 4 parameter model, and I can have a linear relationship between y and the x's, XA, XB and XC. Now the question is, what should we do? When we have done 4 experiments, we get only these 4 constants, and we get some information. Suppose we want to further explore it, I can add one more experiment. Okay, I can add one more experiment and find out whether that experiment is also going to follow this relationship. If the discrepancies are large, that means that whatever interaction effects we left out must be important. That means that the results are going to be dependent on the terms which we ignored earlier, and therefore I have to do one more experiment possibly, or maybe 2 more experiments. That means that the fractional factorial experiment is a prelude to a larger experimental set. So you would like to first of all get an idea as to what factors are important, what factors are not important, and their relative magnitude and so on. For that, this could be a preliminary design, and once the preliminary design gives me some information regarding what is happening, maybe at that time we can go and do more experiments, plan a bigger experimental set and so on. This is one aspect of the problem. Suppose in the 2-level design, we are taking just 2 levels. So let me just explain what I am trying to do by going to the board and give some information. So, we have n factors and we had 2 levels. And we know that we require 2 to the power of n experiments to resolve all the interactions. This is a factorial experiment. But what we were doing is 2 to the power of n minus, let us say, this is a fractional factorial experiment. So, in the case of fractional factorial experiment, I will not be able to resolve all the factors, main factors, then the products and so on and so forth. That means that this is going to reduce the number of experiments. At the same time, it will also resolve less number of factors. So, we say that the P here will reduce. If for example, we had 2 to the power of 3 and then we have 2 to the power of 3 minus 1. So, here how many factors are there? 8 factors are there. Constant x a, x b, x c, then the products of x a, x b, etc., then x a, x b, x c. So, what we resolve here is only 4 factors. Okay. We are able to resolve only 4 factors. So, that means that the number of factors get reduced, number of factors that can be resolved. What I mean is, so resolution get reduced, resolution suffers. This is one aspect of the problem. The second aspect, however, is also equally important. Let us look at that one. If you have only 2 points, let me just draw a simple sketch. I will say x a and let us say 1 factor experiment. So, suppose I do at one low value, high value plus 1, I get two points. All I can do is to join by a straight line. So, this assumes a linear relationship. A linear relationship. Suppose the relationship is non-linear and we want to find out, at least you must do one more experiment somewhere in between. For example, if I do an experiment at some intermediate value, I may get a value here. That means that now you expect the relationship to be like that. Therefore, the factorial design, which uses only 2 levels, can be an exploratory design which gives some information about what is happening, but to resolve things like whether it is a linear relationship or a non-linear relationship requires at least one more experiment has to be done. If I do one more experiment, suppose it came very close to here, then I am confident that maybe the linear relationship is not bad. Therefore, we will say that the levels more than 2 if non-linear behavior is expected. Only then you will be able to find out whether it is non-linear or not. You can resolve only by doing at least one more experiment, at least 3 levels. So, when you go from 2 level experiment to a larger number of levels, obviously the number of experiments will become excessively large. And the second point with respect to these multiple level experiments is that some of the factors may have linear relationship, some factors may have non-linear relationship. If we recognize which are linear, which are non-linear, we may still be able to bring down the number of experiments to some extent. For example, those which are non-linear, I will have to do more experiments to resolve the non-linearity in the dependence, and in the case of linear factors or the factors which have linear dependence, that is the experimental outcome is linearly dependent on the factor, then I can do a fewer number, even 2 level may be able to resolve that. So, the number of levels is something which is to be determined by looking at the behavior, whether it is linear or non-linear, it is going to tell us about the number of levels. So, these are some of the ideas which one must keep in mind before jumping into any experimental activity. Do some exploratory experiments, find out whether linear, non-linear, whether what are the factors that need to be resolved, and once you have this information, we can go for a more complete experimental procedure, experimental program, and complete the experimental activity which we have in mind, and that will give us the maximum amount of information or the amount of information which is required to be obtained. So, with this background, let me now go back to a simple design. In fact, I mentioned earlier on that we will first consider the factorial design, which is usually useful for process modeling and so on, where the outcome is one particular quantity we have in mind, either the quality or some such attribute of a process. But in the case of simple design, the goal is slightly different. We are interested in finding out what is the relationship between the outcome of the experiment and either one factor or several factors. This is a more ambitious program. You are not interested in only one particular operating point or the design point. You are interested also in knowing what is happening for different values of the input. The number of input factors may be quite large. In case the number of input factors are large and the outcome is dependent on many factors, of course, this is a more cumbersome work, but there are some redeeming features which I am going to talk about. So, the simple design is characterized by varying one factor at a time. Suppose there are 3 variables which are going to be affecting the outcome, you vary each one at a time, keep the other 2 constant. Of course, this will increase the number of experiments required. Of course, you can find out which one are dominant, which are less dominant, and of course, reduce the number of levels as the case may be. Sometimes what we do is we simply assume that factors do not interact or interact in a particular way, and then we simplify or reduce the number of experiments. In general, the simple design requires a large number of experiments, and that cannot be avoided. But let me just take a simple example which is shown, which is going to be discussed in some detail for the rest of the lecture. So, we consider a simple example of measuring the friction factor in pipe flow. Most engineering students who have taken a fluid mechanics course would be able to understand what we are going to talk about in this particular experiment. So, the details of how we go about doing experiments in this case are going to be considered, and let me just indicate the type of experimental setup one requires for this. So, what is given is I have got a tube which is shown here, and we can take a circular tube for the present. There is a fluid entering the tube from the left, and it moves along down the axis of the tube. The fluid is specified, maybe it is water or air or any other fluid. Its velocity as it enters is given. Actually, it has to be measured. That is something which we will talk about later. Temperature may be specified, either it may be cold experiment or room temperature experiment where the temperature is not going to change, or it may be temperature is held at a higher value by heating the fluid, in which case it is a high temperature experiment. But in general, when we are measuring the friction factor, we would like to have isothermal flow conditions. That means that the flow is at one single temperature. We identify a certain length of the pipe or the tube as is shown here, and that is the length L, and I am going to put a pressure measuring or differential pressure transducer or differential pressure measuring instrument, and I will get this delta P. This is the outcome of the experiment. And of course, the pipe inner diameter is specified, its surface qualification whether it is smooth or rough is also given. For the present, it is sufficient to look at how we go about doing an experiment, and this is example 9 for our purpose now. So what I will do is, I will go to the board and look at this in some detail. And we will see how to simplify the experimental design. So I will just make a simple sketch here. This is the tube, and the fluid is entering here, and I have identified 2 stations. Suppose I call them 1 and 2, and between them I am going to measure the pressure difference and the diameter of the tube is capital D. As far as the fluid is concerned, we know what is the fluid, what the fluid is, maybe for what, for example, it may be water, and velocity is given as u, capital U I will say is the velocity. We will assume that that is the mean velocity, u is the mean velocity, and we will assume that the entire experiment is isothermal. That means that temperature is going to be constant throughout the experiment. What I am going to do is to look at what are the factors. Factors are nothing but those quantities which are going to affect the outcome of the experiment, and the outcome of the experiment is this. Delta P is measured, that is the outcome of the experiment. Of course, we will later modify this definition slightly. We will see what we are going to look for. The friction factor I am going to look for is F, and we will define it slightly later. So what are the things which, what are the factors in this experiment? We will immediately say that it is a fluid. That means its properties. Fluid is characterized by certain properties, and there may be the density, and in the case of pressure drop we expect viscosity, these two to play a role. So suppose I indicate density by the symbol rho and viscosity by the symbol mu, these two are going to be important. So this is the fluid and its property. Then the velocity, fluid velocity. So this is of course capital U, and of course the length of the pipe and the diameter of the pipe. D. So the number of factors is 1, 2, 3, 4, 5, assuming that it is a smooth pipe. We will say that it is a smooth pipe to reduce the complexity. So we have 5 factors, and this is the quantity which depends on the 5 factors. So let us look at what is going to happen. So we can say that delta P is a function. This is not the friction factor, I am just, this is the function symbol. So we have rho, u, d, l and mu. You can write it in any particular order, it does not matter. Therefore, there are 5 factors. And you will see that if I were to do a factorial design, there will be 2 to the power of 5 experiments to resolve all the interactions. Okay? So we require 2 to the power of 5 experiments. That will be 32 experiments are required in this case. Of course, that is a one way of looking at it. A second way is how to simplify the experiment process. or experimental design. That is the question I am asking. For this, what we will do is, we will look at a different approach altogether to this problem. I am going to find out what is the smallest number of parameter factors that can describe this experiment. Okay? We are looking for the smallest number of factors required to model this. For this, we take recourse to dimensional analysis. Of course, the dimensional analysis for this particular problem has been done long ago by many people who have worked in this area. Therefore, it is nothing new. For the first time student, of course, it is a new activity, and I am not going to indicate how dimensional analysis is done. This is taught in the course on fluid mechanics, and I will simply assume that such an analysis can be done, and the basic idea of dimensional analysis is to go for what are called groups, non-dimensional groups. And in fact, in the present problem, only two groups will be involved. One, the friction factor, and the second one is called the Reynolds number. That means I can look upon the friction factor as the outcome and this as the factor. I call the friction factor a friction factor, but it is actually the outcome of the experiment. And what is the thing which I am going to vary? What is the factor which influences the friction factor? In this case of a smooth pipe, it is only the Reynolds number which is going to affect the friction factor. So, this is already a large simplification. We had 5 different quantity factors which were shown earlier, and now I have come to the conclusion there is only one factor. So, the reduction of factors here has taken place by a knowledge of the concerned field, in this case fluid mechanics, and from the basic ideas of non-dimensional or dimensional groups or dimensional analysis, we are able to reduce the number of groups to just 2. So, let us look at the definitions of these two, so that we will be able to appreciate what is going on. The Reynolds number, which is named after the physicist Reynolds, is given by rho u d by mu. Of course, mu by rho is also given, the mu is the dynamic viscosity. If you take mu by rho, it is the kinematic viscosity, which is usually given by the symbol nu. So, this also becomes u d by nu. The friction factor is actually a non-dimensional pressure drop parameter. And what we do normally is to use the dynamic head which is given by half rho u squared as the measure. So, with this basic idea, I will say that delta P is equal to F L rho u squared divided by 2d, or I can write the friction factor as F is equal to 2d by L rho u squared into delta P. And notice that this is measurable. L, D are the length and diameter of the pipe, which is also measurable quantities. U is also measurable, and therefore, we have to measure these in a particular experiment. Of course, we are measuring a large number of quantities, but we are able to express everything in the form of a simple expression involving only the relationship in the form of two groups. That is the simplification we have been able to bring out. So, in the experimental design, never mind what are the things we are going to measure, I am going to look at only one outcome, which is the friction factor, and one factor, which is Reynolds number. So, the simplification is already apparent, and therefore, it is not necessary to go about thinking in terms of a factorial design and so on, which in principle one can do if one did not know anything about the process. In this case, the knowledge in the field has helped us in looking for the right kind of relationship. Therefore, I will summarize thus. So, we are going to say that F, the friction factor, is a function of Reynolds number, and of course, I do not know whether it is a linear function, non-linear function, we do not know anything about it. That is what we have to find out. And from experience, we know that this relationship is not linear, and there are other subtle features. What are the subtle features? One, Reynolds number is an unbounded quantity. That means it can be any value. It can be without flow. If the flow velocity is 0, Reynolds number is of course 0. If the flow velocity is very high, the Reynolds number can be very large. In other words, Reynolds number range is very large. Let us put it as order 1 to maybe 10 to the power of 6 or even higher, it depends on the particular occasion. Of course, the friction factor is normally a small quantity. Okay. So, if the range of the particular variable is very large, as in this case, it means that it may be difficult to get or cover the entire range by using a single fluid or single diameter and so on. So, that is where the experimental design has to concentrate. Let us just briefly explain that. I will go back to the first slide, where I introduce the idea of flow inside a tube. I will write here a Reynolds number definition is U d by nu. If I have fixed the experiment to be isothermal experiment, the viscosity does not change, because we know that viscosity is a function of temperature, and if the temperature is held fixed, it is going to be fixed. Therefore, I cannot vary this nu. Once I have chosen the particular fluid, value of nu gets fixed. I have, however, control over diameter of the pipe and the u, and of course, diameter of the pipe I cannot change at will. I may be able to get few different diameters which are manufactured and available in the market. Therefore, I can choose a few levels, maybe 2 or 3 diameters I can think of. So, I will write these later on. So, I can think in terms of a few levels for D. U, of course, I can vary over a large range. If I have a good enough pump capable of pumping the fluid through the circuit, I can do it with low velocity by putting a valve, and then by opening the valve slowly, I can increase the flow rate and I can increase the velocity u. Therefore, u can be controlled or kept at any specified value over a fairly large range. Therefore, if I look at the possibilities, D, a few levels are possible. For example, I can take a 10 millimeter diameter, I can take 18 millimeter diameter, I can take probably 35 millimeter diameter. Just 3 numbers just to indicate that a few levels are possible. Even though in principle D can be varied continuously, it is not possible in practice because the tubes available come in certain diameters. In fact, the ones I have given here may not be the correct ones. I am just trying to say that there are only a few diameters possible. Of course, length can be any value. You can have different lengths. L, you can have, again I will say a few levels. The maximum length possible is the length which is available in the market is about 6 or 7 meters, and you can cut it into shorter, smaller length if you want to do that. So, a few levels are possible. U, many levels are possible. So, the point is, if you look at the relationship we have got earlier, f equal to a function of Reynolds number only, okay. The fact that there are only there are only a few levels for D and many levels for U is not going to be a major problem at all. In fact, I can do all the experiments I want with a single diameter pipe and by varying the velocity alone. Actually, I am, in other words, varying one factor. This factor Re, in fact, it will become clear to the intelligent student what is going on. In the factorial experiment, we are talking about the main effects and the interaction effects and so on. Here, it is only the interaction effect. There is no main effect really. The effects are only through products of various quantities. Therefore, Reynolds number involves the fluid property, the diameter and the velocity. So, all these are coming together to give me the effect on the measured quantity. Therefore, it is the interacting effect which is in fact being measured. The main effects are not resolved or need not be resolved because there is no main effect in that sense of the term. So, that is the main difference between what we did in the earlier lecture regarding factorial experiments in the case of machining process, and here we are talking about a fluid mechanics problem, and there is quite a big difference between the two. So, essentially, whether I vary the D and L or only vary U, it does not matter in principle. So, if we are able to cover the range of Reynolds number required in an experiment by varying only one of them, it is sufficient. That is a great advantage in this particular thing, and therefore, what I will do normally is to choose the diameter as a representative diameter, take a suitable length so that the delta p is not very small, I can measure it easily. Then I vary the velocity over a range such that I cover the entire range of Reynolds number. And in fact, by doing an experiment of that type, we get a plot of the following type. It is just qualitative, I am not going to give any numbers here. For small values of Reynolds number, it more or less goes linearly, and at about greater than about 2000, suddenly there is a change in the value, it goes up and then it goes like that. So, we say that this is one regime, we call this the laminar regime, and this is the second regime, we call it the turbulent regime, and of course, there is a confusion here, this we call as a transition. So, what we notice from the outcome of the experiment, this is the outcome of the experiment, and let me briefly touch upon how we are going to perform the analysis. So, I may get some data points here like this, and I may get some confusing thing here, we do not know, and then I may get here some points like this, And therefore, by looking at the data after making a plot, of course, this is a logarithmic graph, I have not mentioned that. If I make a graph suitably, I will see that the data points are going to indicate some kind of a relationship or some kind of a regression model. So, the regression model is a more useful thing to do in the case of fluid flow experiment rather than look for linear models like we did earlier. And there is a big difference between the two models. There the number of experiments and the number of parameters were identical if we wanted to resolve all the effects. In this case, the number of experiments can be quite large, and we are not going to get too many parameters. We want to actually put it all in terms of as few parameters are possible. Okay? If you look at the friction factor data which is given in a book on fluid mechanics, F equal to some constant divided by Reynolds number in the laminar range, and in the case of turbulent range it will be some constant divided by Reynolds number to the power of some value. So, it is a very simple model we are talking about. So, we will say regression analysis is appropriate for this kind of experiment. So, the number of experiments must be so chosen that we are able to resolve the regime. We know that there is a laminar regime, there is a turbulent regime. We must take enough number of data so that we can get some points here and some points in the second regime. Then only we will be able to resolve all these features. And of course, when you talk about the regression analysis, I am not looking for a uniform or one regression equation valid for the entire range. I will divide the range into several regimes or several regions. In this case, I can do 3 regions. The first one is the laminar, second one is the transition, and the third one is the fully turbulent regime or the range, and then obtain 3 formulae, okay, which relate F to the Reynolds number in that fashion. Therefore, the experiment design, this is a simple experiment, not a factorial experiment like we had earlier, because some parameters can be taken only with few levels, some parameters you can take with large number of levels, and in fact many times what we do is to cover the entire range, we may even change the fluid from one which has a lower viscosity to higher viscosity and so on and so forth. So, the Reynolds number being a single factor, it can be obtained by various combinations, and we look for these combinations which give a particular range of values, and therefore we will be able to cover the entire range. So, with this we are more or less we have come to the end of experimental design, and before we wind up this lecture, let me just recapitulate what we have done in the last 8 lectures, which forms one module. In the several lectures we have given, in these 8 lectures, we have started with a general discussion on measurements, their requirement, why we do measurements, what is the goal of experiments and so on. Then we followed it with some ideas about errors in measurement and their ubiquitous nature, that is errors are always present, and there are 2 types of errors, the bias as well as the random errors. We discussed quite at length the nature of the random errors, how to characterize them and so on, and then we have looked at the regression analysis, which is a very important tool for experimental representing the outcome of experiments, and then we talked about design of experiments in process kind of application, where we have a certain number of factors and levels, and we have rounded off with a set of simple experimental procedure where you have number of factors is small, even though number of factors originally is very large, you are able to reduce the number of factors considerably to a small number, and therefore a simple design is adequate for this kind of experiment. In fact, the simple design with enough number of experiments done to resolve some of the features in the result, like we talked about the laminar, turbulent and the transition regime, That is what one should look for. Therefore, experimental work involves some prior understanding or knowledge of the field. Then you must also have all the knowledge about different instruments which you can use for performing the measurements, and then you must have the important tool called regression analysis to interpret the data in a proper fashion. So this will be called as a good presentation of data. When you are able to do regression analysis, put everything in terms of a few parameters and a simple formula, you have been able to communicate your work to the wide audience in a proper fashion. We will stop here at this time, and from the next lecture we are going to start module 2, which will look at measurements of different quantities of interest to us as mechanical engineers. Thank you.